Hello everybody and welcome to session number 10 of my lecture on statistical energy analysis and hybrid methods. This time we talk about waves in structures. So what makes the treatment of waves in structures so complicated? First, just to remember, when we talk about fluid waves, the world was quite simple. We just had one scalar quantity called pressure, which was sufficient to describe the wave field in fluids. When we talk about structures, we have many different wave types, and they have to be described by a three-dimensional displacements in space. So the scalar quantity is now replaced by the three-dimensional vector field, which makes it from this also quite more complicated than in fluids. If we consider, for instance, waves in plates or rods or beams or whatever, we also have to consider the rotations in all three directions as a degree of freedom, making the things or the calculation or the description of such waves even more complicated. However, when we like to understand real constructions, we have a variety of properties and geometries and material. For instance, here, if you can see in this example for a fuselage section, so the material and the thickness and whatever changes a lot. So you will not have, there's just a rare chance that this could be modeled by analytical solutions. But on the other hand, we need those, and we can only provide solutions for simple or canonical systems like beams, bars, rectangular thin planes or membranes. So, and the only way to describe a real system is to use numeric methods. For instance, or which is a typical candidate, find the finite element method denoted by FEM. But if we need a finite element method, why do we have to deal with and discuss and treat structural waves in an SCA lecture? So the reason is quite simple, because we cannot create good or well-designed SCA models or hybrid models if we don't understand the wave motion in structures. So that means a basic knowledge of wave propagation in structures is mandatory to understand the physics. That means to know the wavelength, wave speed, and the number of modes. And from this, to understand the statistics of this structural subsystem. So this is why we are talking about structural waves here in this statistical energy analysis lecture, even if for typical systems we need a numerical method to describe and to model such a realistic system. Good. For doing this, we have to start with some typical basic equations and definitions, and we start with the pressure-like quantity. This is the stress for solids. It's a force that is acting on an infinitely stiff surface of a block, for instance, that's fixed here on ground. The stress is supposed to be positive if it leads to an elongation of this block, which can be seen here now in the updated figure. A normal stress is characterized by the fact that the force and the normal vector is hinting at the same direction. So here in the normal direction of z. The double index here in this sigma symbol denotes that that is a classical direction in z. Both the force and surface normal vector are pointing in z direction. Good. So far for the excitation or the force-like dimension in solids. This excitation or this stress leads to a change of shape, and the main effect is the elongation of the block. And this relative change of the block length is what is called the strain, or the normal strain, or here the strain in z direction. It's a ratio of the change in length divided by the original length. And the symbol is epsilon. So epsilon zz means length change in z direction divided by the original length. The relationship, the material constant that relates both quantities is called the Young modulus, using the symbol E, and that's the ratio of stress, normal stress, divided by normal strain. The stiffer the material is, the higher the young modulus would be. The stretching is at a solid always accompanied by contraction. So if there is an elongation of this block, it gets thinner. And the quantity that describes this effect is the so-called Poisson ratio, denoted by nu. And here the convention is also xy, so that means the ratio of the strain in x direction divided by the strain in z direction is given by xz. We use a negative sign here because the strain in x direction will be negative, and this guarantees that the Poisson constant is positive. Good. So there are other strains possible, and this could be, we could apply a force that is exactly, it's pulling in transverse direction, so here in x direction, on a surface with normal vector in z direction. And this is what we call transverse or shear stress. This is often denoted by symbol tau, but we can also stay with the sigma, as given here by this. Good. So in the book and also in the lecture, I always stay with sigma for all stresses, and the shear effect is denoted by the fact that there is the index is changing. So, and the nomenclature is also the same. That means that the first index is the normal vector of the surface, and the second index is denoting the force direction. Again, this stress has an impact on the solid. It changes the shape, so it's a deformation with a specific angle gamma, and gamma is called the shear strain. If we do it totally precisely, we need the tangents of the change of the delocation of x, or the displacement, and the length of this block in z direction. But for very shear small angles, it is similar, because the tangents for small dx is nearly like the ratio of the x divided by z. And we also have a modulus that defines this ratio between the shear stress and shear strain, and this is what we call the shear modulus, denoted by symbol G, and that's the ratio between the shear stress divided by the shear strain. Good. In addition, we have now to define what is the quantity and how do we describe displacements in our three-dimensional space. So as in the pressure field, the three-dimensional space is usually defined by coordinates x, y, z. And the displacement is now described by u, v, and w. And that means the block here, like here shown on the left-hand side, if you look at the lower left corner, that is displaced by vector uv in the plane. And that means that it's shifted to a new position. And this new position is denoted by x plus u, y plus v, and z plus w. And this is something that you always have to keep in mind. So if you talk about those coefficients, we're never talking about the location. We're always talking about displacement if u, v, and w is used. Good. So that so far for introduction. Now the question is, or that's the job that we have to do. We would like to express the strain in terms of equations that are just related to the displacement. And we start with the normal changes. So just imagine that you have a small slab in the solid located at x with a thickness dx, and if this is moved to another location u by the left side, and the right hand side of this block is located to x plus u plus the change in thickness. And the change in thickness is given by the derivative of u with respect to x multiplied by the original thickness. What is the impact? The thing is that the relative change of this block is simply given by the derivative of u with respect to x. And the same can be done for other directions. Long story shortly told, just the derivative of the displacement coordinates to the related normal coordinate gives us the normal strain. Easy thing. Good. When we would like to talk about the deformation shape on the shear strains, things are a little bit more complicated. And it's a good idea to separate everything like this into different kind of chain, let's say, deformations. And we start with a dilatation. That's just a simple global volume change. So that means if it in 2D presentation is a change in thickness, just adding up the normal strains by the original thickness gives us the change in volume, also called dilatation. The second moment version B is the deformation. That means if you're just pulling here on top of this, we will have a change in the shape. No volume change, but just a change in the shape that comes with the angle of the shear strain multiplied by the length. And the final change no change in shape, but dispositioning more or less, that's rotation. So if we rotate this block, we have an angle here that is given by the rotation angle in Z in the surface multiplied by the length of this block, and in x direction, and the same is true for the upper coordinate. We will finally need this what is the final task? The task is to find an expression for the displacements that relates the angle and this angle to the displacements. So let's see what happens if we combine this thing. So in this upper figure we are neglecting the dilatation, we just stay with the rotation and deformation, and we start with the rotation. So if a block is rotated like this, we'll have those angles beta z and beta z, which leads to this change of v with respect to x, or this change of u, negative here, with respect to y. This is why we apply this derivative. When we, in addition, apply this b case, so that means the deformation, we have the following effect. So the angle is getting bigger here on this area, so which is we are adding the rotation and the deformation, and here we have the other situation, so the rotation is partly compensated by the deformation. Why do we need this? Let's come to the next slide. If we just see what is the change of u with respect to y, it's the we have to take the expression that was shown in the upper figure here. That means that leads to a subtraction of those two angles. And if we monitor the change of v with respect to s, we have to add the angles, which is given by this expression, or leaving the gamma notation by this expression on the total right-hand side. So now we have everything on board with this system of equations to relate it to the displacement derivatives. We start with the difference of both equations. That gives us the rotation, obviously, because the difference kills the shear strain, and that means that's an expression for the rotation. And if we add both equations, we get the deformation angle, or the shear strain. So that means epsilon xy follows by the sum of both equations, which is again expression of the displacements. And the same can be done for other shear angles, which are just interchanging displacement coordinates and the main coordinates with respect to the derivatives of the main coordinates. Good. So, just to note, we have now defined all expressions for normal strains and shear strains. In a full equation, this has to be presented in a tensor or matrix. So this is just given by a symmetrical tensor of second order, which actually is a matrix. And again, we can separate here between the normal and diagonal components if we use the gamma notation. But again, we will mainly stay with this version here, because the shear strains can be easily identified by the fact that the index is not the same. So when we would like to find a way to write this down in a simple formula, the easiest way is to define indices Ej, which could be x, y, and z, and to define the quantities, the displacement by eta with index I, denoting u, v, and w, and the same for the three directions of the derivative. Then we can write down the coefficients of the upper strain tensor by using the below formula and the right-hand side formula for the normal constraint. So by this simple expression, the full strain behavior is given and all coefficients are described. As mentioned, this tensor is symmetrical, and this helps a lot because this That means that those components in this order are independent, and those would be the same like because it's a symmetrical tensor, and this helps us to apply the so-called Folk notation. So this matrix can be written in vector form, and the nomenclature is that we start with the normal components and then with the shear strains which follow exactly the path and it was noted before. So it's not xy in the beginning, it's yz is the component number 4. So far for the strains. Now we come to the stress definition, then we come to a relative change in volume. Sorry, I forgot that. It's just the sum of all the changes in the volume, and that means if we do so, we can it's a change in volume related to the original volume. It's just the sum of all normal strains. By the way, this here on top should be of a volume. This should be not, that should be another way of delta, small mistake, but also good to know. And this could be easily expressed from displacement. That's just the gradient of the displacement, because that's what you get if you apply the nabla vector to the displacement. Good. So far for the stresses, strains and displacements. Now we talk about mechanical stress. As mentioned several times before, we have a normal component, which it means with a parallel vector of normal vector and the force. And we have the pointing at the same direction, and we have the shear stress, which is the tangential force or the normal force that has a normal force with relationship to the normal vector of the surface. So how could the full stress state of a solid be given? Just have a look at the cube as shown here. And all the cube is located in parallel to all the classical Cartesian axes. And we see that we have all the three surfaces, the normal vector x, y, and z. And that means that the first index in our stress component, as explained before, denotes the direction of the surface of the cube. So this is the z denoted here. By the way, this should be x, but that's a small mistake. And the second index denotes the direction of the force. So that means if we have the same index, that's denoting the normal stresses, and if the combined index, that's denoting the shear stresses. This is why we don't need the tau convention. And this is just writing again down the convention of the stresses using this formulation, which is slightly easier than the strain formulation. Good. Again, we have a so-called condition of moment equilibrium, and from this it would follow that if we exchange the indices, the indexes, the components must be equal. This helps a lot because we have the same thing like for the strain tensor. So we again ending up with a symmetric matrix or with a symmetric tensor of second order. And we can again apply the Folk notation with the same convention. So the path goes like this, and we have replaced this matrix by a 6-component vector. Good. So far for stresses and strains. Now the question is, how do we relate the strain to a stress? That is similar to the question, how do we relate the pressure to a change in density by fluids. So we need a material, in other words, we need a material law. And this material law in solids is called Hooke's law for a linear elastic media. And normally, if we stay with a tensor version, it would be given by this quite complicated structure, and the relationship between the stress and the strain would be the stiffness or elasticity tensor, which is the fourth order tensor. Or the other bidirection, it would be the compliance tensor. Quite unhandy, quite complicated, and this is why we are not using it, as mentioned several times before. Also, those tensors which have 81 components can be reduced to 36, because the symmetry also holds for this tensor here. And with a Folk notation, we are ending up with a stress tensor or with a matrix that has 36 components, which is still a lot. But don't panic. In most cases, things are not that complicated. We just have made two practical cases, and we are using here. We have normally, in 99%, we have isotropic material, like steel, rubber, aluminum, which simplifies extremely this expression on top. Sometimes we have autotropic material, that's something like carbon fiber, reinforced plastic, plywood, etc., which is also a little bit more complicated, but as you will see, we would have still lots of zeros here in this full tensor or vector matrix description. So, as mentioned, we stay with isotropic material because that's even complicated enough, and we start with the Hooke law of with the Young modulus that we have already implemented. So if you remember well, for the normal stress in x direction, we had this expression, but this was an expression for a small block. So that means the stress leads to a thinner block. That means this block was not constrained. But now if we have a full material, the block is constrained. That means if we pull at this block, it is constrained by all the other direction, and the Poisson ratio leads to a, let's say, compensating stress. So it's a stiffening effect. So we have to subtract from the first equation the component that's created by the constraint. And this has to be done for all those equations. So if the x direction is constrained by yz, and vice versa for all the other two directions. As usually, we can also apply shear stresses. Here the word is quite simple because there is no volume change, and that means we can stay with the original definition. So we have a shear modulus, and it's always the same because we're talking about isotropic material, and the shear stress and the shear strain are related by the shear modulus denoted by G. Good. However, those quantities E and G, they are not independent or nu. They are linked by the following equation. So that means E and G, if E and G are given, we can automatically calculate the other third constant or vice versa. That's something that you also have to keep in mind. Good. How would the compliance and stiffness matrices look like using this material laws? So you see, and that's very good, that there are lots of zeros. So all the 36 components are in many cases the same. So we have the same here on the diagonal. These are the same. So we're ending up logically, because we have three constants, we're ending up with exactly 3 coefficients in the compliance matrix. And in the stiffness matrix, that's the same. We also have 3 constants. Please note that all the other, lots of this matrix constants are 0, simplifying things a lot. Good. So we now have everything on board. We have defined the strains, so the change in shape of our solid. We have described the stress vector or stress tensor, and we have defined the material law. And now we have everything that we need to formulate a wave equation. And this is what we do next. So, as mentioned, there are several modes of wave propagation, so just a hint that things might get a little bit complicated. So, normally when we talk about structural waves, the wave type depends on structure geometry. It's really a difference. It makes a great difference if it is an infinite bulk material, as the Earth for geophysics guys, or if it's a flat or curved plate, or it's a beam or rod. This makes this something that we really have to consider. So the wave equation is determined from the material laws, and again, to keep things simple, we stay with isotropic materials. Good. So we use our stress balance and the cube with lots of control surfaces, as we have done this also for the fluid equations. Just imagine for the force in x direction, it follows from the difference of the stress, normal stresses on both sides of the cube, but it also follows from the normal stresses on the other sides, because we have now shear stresses, which also lead to force in x direction, because that's the relationship of the shear stress. So this is why we just, in the fluid world, we just had the upper equation using exchanging this by pressure. But in a solid, we have also the shear component, which makes the world a little bit more complicated than in the fluid world. If we apply Newton's law, so that the force is acting at a mass element and leads to an acceleration in u direction, and we estimate this mass by the density and the size of our cube, then if we just divide the upper equation by this volume, we are ending up with we end up with the, let's say, the change of the shear stress, which is the normal stress, which is given by this quantity. And if we just add all the forces up here, as we should do, then we would get the following expression. So that means the change of stress with respect to x, y, and z for the normal and the related shear stresses gives the acceleration of a mass element in x direction. And the same can be done for the other two direction, leading to further expressions. Good. So far so good. So this would be, now this is just the Newton equation formulated for solid material. The question is now how can we create a wave equation out of this? And the job to do is to replace all this sigma expression by other expressions that are related to displacements. And we need the material laws for this. That's what we have to do to get rid of all the stress formulations here on the left-hand side. So for doing this, we start with the equation 136, and we just adding all those equations in this line, and then we're getting this expression here. Some of those expressions you should already know. So this is the dilatation, as it was shown before. And if we use the expression that relates the Young modulus to the shear modulus, so we get rid of this E here, the Young modulus here, then we get this equation here. So that's the next step. So then now we would like to find an expression sigma for sigma x, and now we start with the left side of 126 again, which was this expression. Just remember that's the Young modulo, the Hooke's law corrected for the solid material of the constraints. We solve this for sigma x, and then we add the term nu sigma x on xx on both sides, and we would get this expression here. Good. So when we apply 129, so the upper equation, then we get the following expression. And what do we have here now? We have now an expression of the normal stress on the left-hand side, and on the right-hand side we have exclusively only expression of strain or displacement. So that means we are now getting rid of all our stresses. The same can be done for all the other directions, or we can write it in a different formulation. If we eliminate E again, we would get this expression using the shear modulus, giving us then the following expression, and we just exchange the strain formulation by an expression that is directly relating to the displacement again, because this is equal to this. Good. So we have done this for the sigma x in normal direction, and it could also be done for the others, the y and z. But now it's time to introduce some new constants, which we call Lamé constants, lambda and mu. And sorry for using lambda for another purpose, but that's a normal constant for Lamé. It's not a wavelength here, but it's the only session where we use lambda, not in the wavelength context. This lambda is an extension, is a measure for the extension perpendicular to the stress. This is one of the, let's say, explaining expression for this lambda constant. Mu is quite simple. It is equal to the shear modulus. If we put this constant into the equation 130, we would get this formulation. So you see why we use that. So we're getting this combination of expression is now just expressed by lambda, making this equation quite more handy. As mentioned before, the same equation holds for all the other direction, but we have to exchange coordinates a little bit. So now we have x, y, and z on board. The remaining shear stresses that have to be found are the shear stresses, and that's an easy thing. Here's the relationship is just given by the Hooke law, which gives the shear modulus and the shear strain that relates the shear stress. Good. So now we have explained all stresses in terms of displacements. So good, we can use this and enter this into our existing equation, so the 1D Newton law. And then we would get for the x direction this expression, just using all those above definitions of the stresses. And for all the other the direction, you would get other expressions. So, but quite similar logically. If we write this all together in single vector form, we will get this final equation here. The good thing is now that we just using the displacement vector. So in this expression there is no u, v and w again anymore. We just have a quite handy expression of the just using the displacement vector. When we use the identity as given here before, we can slightly modify the upper equation and we get this expression here. So we just removing this part or exchanging this part by this part. Why are we doing this? And that's quite simple. The idea, as mentioned, we have many modes of wave propagation and we need a way to separate them both. And we can now separate this into a kind of, let's say, okay, by finding two different ways. And one thing, if we assume that we have a gradient-free displacement field, this would be 0 in the upper equation. But it could also happen that we are looking for a field that is rotation-free. We have no rotational motion in our displacement. This would give an equation where this would be missing. So this is why we're using those two different equations to separate the wave modes. Good. Anyhow, the upper equation, it can only be solved analytically for simple geometries. And to my knowledge, it's infinite world or maybe semi-infinite world or maybe a thin infinite layer. This is where this is solved. I don't have any other options where we are ending up with handy analytical solutions. Good. So, but as mentioned, we have two different operators here in this equation. That means that we have, this is a note that there must be two wave types in this solid. And if we separate this vector field of displacement into an irrotational component, which is given by the fact that the curl of the displacement is 0, or on the other hand, to use a ds component that is characterized by a 0 divergence, we can, the sum of both of them gives the final dilatation. That means, but on the other hand, if we take the gradient of the displacement, we would just stay with the shear component, and if we take the divergence of the longitudinal version, we would also use we just end up with a longitudinal version. So those are, as mentioned, are independent wave times, and we call them longitudinal and shear waves, and you will understand why they are called by those names when we look into the next slides. So the longitudinal wave is characterized by the fact that it's rotation free. So nabla cross d is 0, and then we use equation 134, so the second of both equations, and we are ending up with this wave equation for the displacement. So the quantity that defines the speed of sound is the longitudinal wave speed, which is given by this constant. So a combination of all material constant, and as we see, the stiffer the material it is, the faster the velocity is, the heavier it is, the slower. Somehow similar to the equation for the sound speed in fluids. Good. As mentioned, longitudinal wave speed, and this is also very important. That's the highest speed. In a solid material, this is the wave speed that has the highest speed. When we assume that we have no motion in v and x and in y and z direction, and we assume that there is no change in y and z direction, we ending up with this equation. So it's just dependent on x. The only shape in displacement is u, and the wave shape would look like this. So the direction of the displacement goes into the direction of propagation. So in u is the shape and x is the direction. This is why it's called longitudinal. We can also apply the typical harmonic wave equation or solution to this, and that means we would have a propagation, a wave number, and longitudinal wave number, which has this quantity, and that would also lead to the shape here on top of that. Just to give you an idea of some figures, in steel at 500 Hertz, you would have a wavelength of 10 meter. So maybe it's worth mentioning. So this is the reason, but in technical systems, this mode of wave propagation is not that relevant. Not for our construction material. The situation is different if we talk about soft foams or whatever that's used as house insulation material. There we have quite low speed of sound, speed of wave speed, but for technical materials it's super high. So not relevant to be considered only at very, very high frequencies. Okay, so far for the longitudinal waves. Now we come to shear waves. We have to take now equation 133. And we know that the gradient of the displacement is 0, and this gives us this wave equation, and we have now the shear wave speed, which is denoted by this quantity. So it's the shear modulus divided by the density, and that is the shear wave speed. So it's slower than longitudinal waves. That comes from the definition from the relationship between G and the modulus, and there's no change in volume. It's clear. It's definitely given by this. So this is isovoluminous, and the particle motion is transversal to the direction of propagation. So it moves in this direction, and the wave goes into this direction. And this is why we call this a transversal or shear wave, because it's related to shear motion. When we again say now, okay, the displacement in u and v is supposed to be 0, and the change in y and z is supposed to be 0, and we consider the equation here, the condition above that there is no, it's dilatation free, we could simplify this to this one-dimensional wave equation, which relates the displacement in z direction of w to x and to this wave equation. And the solution of this would be, again, the harmonic solution. So now we have the wave number, the shear wave number with this quantity, and again showing the same table than before. You see roundabout the shear speed is half of it, depending on the Poisson constant, but usually it's somehow near half of it for typical examples. It's slower than the longitudinal wave, but still, if we look at the example for steel, 500 Hertz, it's still a large wavelength. 6.4 meter, that's still too big to be considered in a small system like a car or whatever. Good, so far for solid waves in the bulk material. Good, so that's it. It gives you an idea about how structure and motion are described, what are the basic equations of motion. The next session will talk about a much more important and more realistic system in technical constructions. These are plates. So in plates we have now to consider the rotation, and plates are heavily used in any constructions. You could call it a wall. It's the sheet of metal that creates a car body of a car, of a ship, of a plate. So plates are definitely something that are much more realistic and must be considered in our simulation world for vibroacoustics. I hope you enjoyed this lecture. The next lecture will be, as mentioned, about plates, and I wish you a nice time. Have fun with this lecture, and see you for the next session. Bye bye.